In my Structural Engineering Made Simple series, today I would like to talk about design of shelf angles. Please take a moment and read the disclaimer at the bottom of this slide before we start. Shelf angles, also referred to as steel relief angles, are secured to the structural system and are designed to provide support for facades such as veneer walls. Usually they are installed at every other floor level. Therefore, each shelf angle carries the weight of 2 stories of the veneer wall. The following is a vertical detail of a veneer wall with a shelf angle supporting it, and the attachment anchors to the structural system. Some architectural features are also shown. Here is a shelf angle shown in red, and the anchor bolt securing it to the structural system. Architectural features shown are the sealant and backer rod, the flashing, and the anchor to prevent wall movement. Shelf anchors are designed for the dead load of the veneer walls they support. Their design includes sizing the angle for support of the wall, designing the angle for proper thickness, and designing for the connection that attach the angle to the structural system. When the supporting structural system is a masonry wall or a reinforced concrete frame, the attachment of the angle to the structure is achieved by using anchor bolts. Proper design of the anchor bolts requires selecting the anchor cross-section diameter, embedment length, and the spacing between anchors. When the structural system is a steel frame, the angle attachment is done using welds or bolts. The design then requires selecting the weld size and weld length. Bolt design requires selecting a proper cross-sectional diameter for bolt A325 or A490 type, following design provisions of the American Institute of Steel Construction, AISC. Pertinent references for design of the wall, size of angles, anchor bolts, welds, or connecting bolts are provided below. We also use these references to prepare this video. Sizing the angle. The angle must have an adequate width to safely support the wall. In the longitudinal detail shown below, notice that the weight of the masonry wall is treated as a uniformly distributed load. The anchor spacing is S, and the edge distance, that is the distance between the center of the last anchor and the end of the shelf angle, is shown with S sub E. And here is the cross-sectional detail of the shelf angle. Notice that the load from the weight of the wall is acting at the tip of the outstanding leg of the angle. We're going to talk about this a little bit more later. Also notice the forces in the angle. There is a tension in the anchor and there is a shear in the anchor. Furthermore, there is a compression at the bottom on the support. As a conservative design practice, the load W from the wall is applied at the tip of the angle. A more accurate modeling is to take the point of application of the veneer load at the center of the wall at the distance E from the center of the vertical leg of the angle. This is shown in this figure. Therefore, the determination of dimension E is important. Dimension E is computed based on the brick block dimensions and the fact that at least 75% of the thickness of the wall needs to be supported. Here you see the dimensions of a brick, 8 inches by 4 inches by 2 2/3. Usually, a veneer wall has about 4 inches of thickness. In calculations, the effective thickness of the wall is used, which is 3/8 of an inch less than the nominal thickness T. In this figure, you notice that the brick wall needs to be supported at least over 75% of its effective thickness. Also notice that only the flat area of the angle leg is used to support the wall. For a 4-inch angle, the flat area is 4 minus 5/8 of an inch, as you can see in this detail to the left. Finally, when we put these numbers together, we should be able to determine that dimension E. We're going to talk about this a little bit more. So again, for the 4-inch angle, in the example we provided, considering that the 75% of the effective thickness needs to be supported, we can compute and find out whether we have enough area, the flat area, to be able to accommodate the 75%. The effective width of the wall is 4 minus 3/8 of an inch, so it's 3.625 if it is a 4-inch thick wall. If an angle with 4 inches of outstanding leg is used, the flat area of the angled leg is 4 minus 5/8 of an inch, which is 3.4 inches. 75% of the effective wall thickness is 0.75 times 3.625, which is 2.72 inches. Therefore, you notice that the angle is okay. We only need 2.72 inches and we have 3.4 inches of area. However, this condition provides only a very small gap area between the veneer wall and the inner faces of the vertical leg of the angle, about 1 inch. In practice, this gap is wider and is about 2 inches. In this situation, certainly a larger angle size, for example, an angle with 6 inches of horizontal leg, will be needed. Here we provide the detail again, and you notice how the 2.94 is computed. Please notice that this dimension is measured from the center of the thickness of the vertical leg of the angle. Also, if you are looking for this dimension 5/8 of an inch to compute the flat area of the angle, for other size angles you need to consult with the AISC manual. In general, if a cavity gap equal to little c is used for an angle thickness equal to little t and the effective wall thickness of t sub e, the distance e is te divided by 2 plus c plus t over 2. Obviously, with a larger cavity gap, the size of the angle will need to increase. For example, with c equal to 2 inches and an angle thickness of 3/4 of an inch, the distance E is 4.19 inches, and certainly we need at least an angle with outstanding leg of 5 or 6 inches to accommodate this. Structural design of shelf angles. For a shelf angle anchored to a masonry wall or to a reinforced concrete structural system, the structural design of the angle is performed for the angle thickness to determine whether it is adequate, the anchor spacing, and the size and embedment length needed for anchor bolts. In this video, we only cover items 1 and 2. Information for sizing the anchor and its required embedment length can be found in documents from American Concrete Institute, ACI. Here is a detail showing design parameters for a shelf angle. Notice that the total load is a uniformly distributed load over the length B, which is equal to 4t. B is the effective length of the angle. It is taken as 4 times the thickness of the wall. However, it cannot exceed S, which is the spacing between the anchors. To the right, you notice another detail showing a cantilever system. This is a cantilever idealization of the outstanding leg of the angle. We use this one in order to determine the required thickness of the angle. The cross-sectional area of this cantilever is a rectangular area B times T. T is the thickness of the angle. And also notice that the load, which was acting at the tip of the angle, is now moved to inner area at the distance E from the support. The load calculation is done for a length equal to the anchor spacing S and a wall height equal to H. However, calculation of all cross-sectional properties are conducted for an effective angle length of B. And as we indicated before, B is equal to 4 times T limited by S. This is an important point to remember. Even though we have referred to B as effective length, in reality, and as shown in the previous slide, When computing the cross-sectional properties of the outstanding leg of the angle, this dimension is considered the width of a rectangular section B times T that resists the bending developed in the section because of the load W. And again, notice that for the purpose of computing the required thickness of the angle, the outstanding leg of the angle is treated as a cantilever beam under the load W. Based on the anchor spacing and using the masonry tensile capacity in bending, we can determine the relation between the height of the masonry and the anchor spacing and decide whether the masonry is able to support itself between two adjacent anchors. As was shown in the longitudinal detail, which is again presented below in a smaller scale, the wall weight is a linear load assumed uniformly distributed. Considering a wall with a height of h spanning over a distance s between two adjacent anchors, the uniform load from the wall and the bending moment developed are: the load is q equal to omega h, bending moment m is equal to q s squared over 8, which is equal to omega h s squared over 8. And in these equations, little omega is the wall density, and for a 4-inch thick wall is usually around 42 pounds per square foot. And h is the wall height. Notice that the wall vertical cross-section will resist this bending moment m. For a wall with the nominal thickness of t, the effective thickness Te, which the effective thickness is t minus 3/8 of an inch, the section modulus would be T sub E h squared over 6. And the bending stress at the vertical cross-section of the wall, which would be affecting the mortar, is little fb equal to m over sx, which is equal to 6 omega s squared divided by 8 T sub E h. Finally, denoting the allowable bending stress for the masonry parallel to the bed joint as capital FB, the design is then described through the expression little fb smaller or equal to capital FB. Therefore, 6 omega s squared over 8 T sub E h is less than FB. Solving this inequality for s results in the following equation for the maximum limit for the anchor spacing. In other words, the maximum opening span to allow for the veneer to support itself. S is limited by square root of 8 T sub E h FB divided by 6 omega. A conservative value for FB is 15 psi for type N mortar, although higher values are considered to be more reasonable. For example, for a wall of 4 inches of nominal thickness and h equal to 15 feet high, as we indicated, the effective wall thickness would be 3.625 inches. And with a density of 42 pounds per square foot, working in inches and pounds, the density would be 0.292 pounds per square inch. And using the equation for S, we find that limit for S is equal to 17.6 feet. This means the wall is able to support itself over a length of 17.6 feet. The spacing that we select for the anchors will need to be less than this limit. As seen in detail below, a portion of the wall will cantilever itself where the latch anchor is located, denoting the distance between the center of the latch anchor to the edge of the angle as S sub E. The wall moment over this cantilever is m equal to q se squared over 2, which is equal to omega h se squared over 2, and the corresponding stress would be m over sx, which is 3 omega se squared divided by T sub B h, and this has to be less than capital FB. Again, solving for SE, we find out that the limit for SE is T sub E h FB divided by 3 omega. For example, if an edge distance equal to 1 foot is used, using the previous values for T sub E, h, omega, and FB, this equation results in a maximum edge distance of 8.8 feet, which indicates that wall is certainly safe cantilevering over the edge distance of 1 foot. For determining an appropriate angle thickness to support the weight of the wall, the outstanding leg of the angle is treated as a cantilever beam as we indicated earlier. Again, we are showing the detail here. The cross-sectional properties of the cantilever are: area is b times t, moment of inertia is bt cubed divided by 12, and section modulus is bt squared over 6. Basic equations needed for the computation of internal forces and stresses are: moment is W multiplied by E, shear is W, and the deflection is WA squared over 6EI times 3A minus E. This is the deflection at the tip of the angle. The applied stress is M over Sx. The applied shear is 3V over 2A. And the design is generally done for bending moment. Once an appropriate thickness for the angle is selected, it is then checked for shear and deflection. However, we would like to indicate that shear is usually not critical. Using the load and resistance factor design LRFD method, the design equation is represented by mu less than or equal to phi mn. Mu is the factored applied moment, mn is a nominal bending capacity, and phi is a capacity reduction factor, which is taken as 0.9 for flex shear. Since the weight from the wall is all dead load, using a load factor equal to 1.4, the factored applied moment is mu equal to 1.4 W times E. However, in computing W, we do some modifications. We are also going to add the weight of the outstanding leg of the angle to the total load. Therefore, W is omega times H plus QA multiplied by S for a wall height of H. Little omega again is the wall density, and Q sub A is the weight of the horizontal leg of the angle in the units of pounds per foot. Finally, the nominal bending capacity, considering the yield capacity of steel Fy, would be from the following equation: Mn equal to Fy times Sx. Using the design equation mu less than or equal to phi mn, we can show that an equation for the angle thickness is T larger or equal to square root of 8.4 times omega times H plus QA, then quantity multiplied by S and multiplied by E divided by phi Fy B. It is noted that by equilibrium, the vertical leg of the angle will also be under the applied moment mu. In addition to the bending stresses, this leg of the angle is subject to a tension stress as follows: little ft equal to 1.4 W divided by Bt, which is equal to 1.4 times omega H plus QA divided by Bt. This stress value needs to be checked. However, usually it does not add any appreciable value to the bending stress. Now let's look at an example. We have an angle 6 by 6 by half an inch used as a shelf angle to support a 4-inch veneer wall of 13 feet 4 inches in height. The cavity gap is 2 inches. The spacing for the anchor is taken as 4 feet. Therefore, S is equal to 4. We want to determine whether the anchor spacing is adequate for the veneer to support itself. We also would like to determine whether the angle thickness is adequate. We want to compute the additional tensile stress developed in the angle's vertical leg. And finally, we want to compute the deflection at the tip of the outstanding leg of the angle. So we know that the effective thickness for a 4-inch thick wall is 3.625. Furthermore, the density would be 0.292 pounds per square inch, and H would be equal to 13.33 feet for 160 inches. Plugging these numbers in the equation for S, we ended up with 16.6 feet, which certainly is larger than S equal to 4, so the spacing selected is acceptable. We continue with the rest of the problem. The effective length of the angle B is 4 times 4, in other words, 4 times the thickness of the wall, so it is 16 inches. The angle selected has a total weight of 19.6 pounds per foot. Therefore, Q sub A is 19.6 divided by 2, which is 9.8 pounds per foot. With 2 inches of cavity gap, E is equal to 4.06 inches. And plugging these in the equation for the thickness that was given before, we end up with 0.39 inches of thickness. And because the angle has half an inch thickness, therefore our design is okay. Continuing with the problem, the factor additional tensile stress in the vertical leg of the angle is obtained from the equation that we gave for Ft and turns out to be 399 psi, and this value is really negligible compared with the factor bending stress. Finally, now we find the deflection. For B equal to 16 inches, the moment of inertia is computed for a thickness of 0.5. Moment of inertia, therefore, is 0.167 inches to the fourth. Now here we recompute the weight. We take the load factor out because for the computation of deflection, we do not use load factors. So the total load W is 2,279. And for the distance A equal to 6 inches, plugging these numbers in the equation for deflection, working in pounds and inches, we end up with very small deflection, 0.03 inches. Some specifications indicate an allowable deflection of L over 600 or 3/8 of an inch. However, they mention that this is for a structural system supporting veneer walls in which L would be the spacing between columns at the perimeter of the building. However, no specific limit for the deflection of the tip of the outstanding leg of an angle is specified. In the lack of any information, if you accept the 3/8 of an inch limit, the deflection therefore should be okay. Please remember that we need to control the deflection so prevent any cracking in the wall. As a continuation of this series on shelf angle design, we must consider designing the anchors as well. Anchors are designed for their diameters and embedment length. Most anchors available today are off-the-shelf products by several manufacturers. These manufacturers often provide the technical assistance and specifications for design of their products. I hope that you enjoyed this video. Thank you for watching.